Thank you so much for doing this interview with me. It's nice to meet you.
It's my pleasure. It's nice to meet you too.
My first question to you is, what is the best way to explain the Million Year Ice Core project to someone?
Right, good question. The Million Year Ice Core project is about reaching as far back in time as we possibly can with ice from Antarctica. And reaching back in a way that gives us a continuous record from the surface, from the last time snow fell Antarctica, which might be like a couple of weeks ago, right back to snow that fell at hopefully 1.5 to 1.6 million years ago. And that time frame, people are like, what does that mean, 1.5 million years ago? It's sort of a significant period compared to the timescales of human evolution. 1.5 million years ago is Homo erectus times, and then as we're getting closer towards the surface in Antarctica, we pass through the first appearance of Homo sapiens about 300,000 years ago, and then we pass through the time of the loss of the Neanderthals, like 30 to 40,000 years ago. So it covers that period, and it covers a period when the climate system has oscillated, has changed back and forth between conditions where there was huge amounts of ice on the planet, thick ice sheets over North America and over Europe, which then melted away and then regrew on cycles that match changes in the Earth's orbit around the sun. And throughout that period, the timing of those ice ages changed. That's what we want to understand, why it changed. And the ice cores also let us put current changes in the atmosphere and in our climate into a context that then spans the whole period of human evolution to see exactly how unusual it is.
Yeah, wow. Very, very fascinating.
Yeah.
So how did you come to be a part of the project, and what does it mean that you are the project leader? What does that mean? What does that entail?
Yeah, so my pathway to coming here was I'm a simple farm boy by my roots. I grew up on a dairy farm in southwest WA.
Yeah.
I always had an interest in science. I think from primary school I wanted to be a scientist, and I did experiments on my kitchen stove and things like that. I remember sort of getting a little bit of trouble sometimes because some of the experiments get a bit messy. And as I went through, and I was quite good at chemistry and physics and maths, and I then went on to university where I studied chemistry and hydrology. And then I think I actually saw a poster on the wall at the University of Western Australia where I went that said, "Not all chemists wear white coats," and there was a picture of chemists working in Antarctica. And so sort of what I've ended up in is chemistry of ice that gives you information about the history of Earth and of the Earth system. So I got pretty inspired about that, and I was very interested in global change. And back when I was in primary school in the 90s, it was an issue. I remember doing assignments on global warming back in the 95 or something, and then as I learning more about it as I went through university, and then learning the key role that the ice cores play in this science. The ice cores being the only way that we can actually measure changes in our atmosphere in the past, because the little bubbles are still there trapped in the ice.
Yeah.
So from Western Australia, I came over to Tasmania to do an honours degree after university. I contacted the people here and said I was interested. They said, "Oh, we've got this project where you could look at ice cores and learn about changes in the sun in the past." And I thought, well, that sounds cool. So I came over for a year to do that and sort of got the bug. I went off and travelled and did some other things, and then I came back to do a PhD here, which followed a trip to Antarctica where I sort of acted more as an assistant, a lot of digging of snow and putting up tents and manual labour out in Antarctica, and that sort of blew my mind. It's just so amazing to go to Antarctica, particularly the first time. It's like no other place. It's almost like if you'd never seen water before or something. You can imagine how you'd just be like, well, this is just stunning. And being in Antarctica and being the vastness of it and the harshness of it, and the coldness and it just has an effect on your senses that's like no other place. And that got me hooked on, and sort of the adventure of it as well. It's pretty tough conditions out there. For us core work, we're out there in tents. So that made me think, yeah, I want to pursue a career in this and sort of combine science with an element of adventure and an understanding of Earth history and of the natural world. And I thought that was ideal for me. And so I did my PhD, and then for a research career, the usual path is then you do what's called postdoc. So after your PhD, you go and study in other international labs and do research. And I went up to America for a year and a half in Seattle and did some work there, which included some trips taking ice cores in the Rockies. And then I got a postdoc in Copenhagen in Europe with my partner. And we both moved over there, and I did some work in Greenland, ice core drilling with the Danes, who were the leaders in drilling ice, and that comes from their connection to Greenland. Greenland being connected to not physically connected, but under the administration of Denmark, although independent as well. And I always wanted to come back to Hobart and Tassie, and the job came up looking for a leader of this Millennium Ice Core project on the science side, and I applied for that, and I was excited and lucky to get that position, which is an ongoing position here at the Antarctic Division. And what it means is that I'm sort of in charge of making sure our laboratories are ready to receive the oldest ice in the world and be able to get the measurements out of it that we want to get, which is measurements of the gases and of the past CO2 and methane levels, making sure we can get measurements of past temperature from the ice, and making sure that we can collaborate well with other leaders in the world in this sort of science to make sure we're at the cutting edge, and that we make the most of this opportunity where the government and the Antarctic Division has come in to support us with this, what is a super massive project. Like the location is 2,000 kilometres inland from the coast of Antarctica, sorry, 1,200 kilometres inland from the coast of Antarctica. So just getting up there is a big challenge. It's 1,200 metres above altitude. We've got a lot of equipment. I've ordered 250 tonnes, a lot of tractor power to get that up there. And so that logistics side is not something that I'm in charge of, but of course the logistics hinges around providing that support to be able to do the science and recover our ice in an uncontaminated way, and keep our scientists safe and have this, the power we need up there, and the ventilation systems, and our ice storage and transport. So I do work closely then with the logistics people as well. Yeah, so it's a busy and challenging job, and it's going to be a long job because it will take us at least 5 years to drill to get to the bedrock, potentially starting around this coming Christmas, drilling of order around 100 metres a week, and we can only really be there for about 6 to 8 weeks a year. Otherwise, it gets so cold that it gets into the minus 50s, and we'd be flat chat just staying alive. Sorry, that was a very long answer.
No, it was good. It was very good. Would you be able to please explain to me in the simplest way possible
Yes.
what an ice core sample is and how it is used in understanding human versus natural climate change?
Oh, that's a good question. So all of the ice in Antarctica fell as snow at some point in the past, and the ice that fell longer ago is buried deeper in the ice sheet, and to the point where out in the middle of Antarctica, where it's 3 kilometres thick, we can get back, we think, over 1 million years by drilling a column down through the ice sheet. And then as the snow is falling in Antarctica, there's, as you know, when you've made a snowball or you see snow, if you've been to the snow, there's air, right, in amongst the snow. But in Antarctica, as the snow gets buried, that snow turns into ice, and the air that was mixed in with the snow gets locked into these ice bubbles, and is like this perfect sample of the atmosphere in the past. In fact, if you'd had scientists in Antarctica, like taking little bottles of air for the last million years, they couldn't do as a beautiful and precise and clean job as the ice sheet does for us, just by the nature of how it forms. And so how does that teach us about climate and human influence compared to natural influence? So the ice core record prior to industrialization, we can see how temperatures vary because we can look at isotopes of water, which are basically like a thermometer. As they change, they tell us temperature. And we can see the gases from the bubbles, and so we can see how CO2 is varied. And if you look at that data, and it's just a measurement, what you'll see is that over our current longest ice core record for 800,000 years, CO2 levels and temperature have varied pretty consistently within a band. From CO2 is like from 180 units during the coldest ice ages up to about 280. And then what we see through the ice cores is that as soon as we get to the Industrial Revolution, CO2 starts to go steeply up, and it goes up way beyond anything we see in the ice core record. And it goes up at a speed that's 10 to 100 times faster than anything natural in the ice core record. And we can also measure really carefully the CO2 that we extract out of those bubbles, and we can see that it has a particular composition, the isotopes, that mark it as coming from fossil fuels, because fossil fuels are more depleted in carbon-14 because they're old. So we can see that the CO2 post-industrial revolution has this really old signal of fossil fuel in it, and it also has some other isotopes that mark its origin. So the ice cores set the context of this is what climate usually does, and then we see industrial revolution and bang, like we're heading outside the natural range. And it also lets us see how closely coupled greenhouse gases and temperature have been in the past, which allows us to estimate the sensitivity of climate to CO2 by looking at that relationship in the past and projecting it forward. And so even without any sort of climate models, just looking at the past, we can say that a doubling of CO2 would warm the planet by around 3.5 to 4 degrees. So I think ice cores and other geological records are a really nice way of using the Earth itself as an experiment, like as a natural experiment, how it changed in the past, what caused it, and ice cores are a really neat way of doing that. And it's just measurement, it gets a bit annoying when you have the climate skeptics and deniers talking about or their view of science and not trusting it, when what we're doing, we're working hard, we're going down there, it's freezing cold, we're drilling ice cores and we're just measuring them on the instruments, and the results are really clear, we're outside the bounds of natural variability.
Yeah, absolutely. So once you extract, hopefully, this million-year ice core, what would be the aim or the information and benefit you want to get out of this? Is it just finding out how far back our humans have impacted on climate change and stuff, or is there another goal in mind? What would we do with the information?
Yeah. So some specific questions that we want to answer with the oldest ice core are that the oldest ice core will take us into a period of time when the ice ages happened more quickly, and we know that from looking at marine records, which give us some idea of past temperatures, but the marine records don't give us CO2 levels, and so we want to see whether past greenhouse gases played a role in the ice ages and interglacials happening much faster during that period of time, or whether it was instead something else. And there's other theories that we want to test, whether it was a change in the material that's beneath the big ice sheets, particularly in the northern hemisphere. There's a theory that long ago, beyond 1 million years, the ice sheets were, during these cycles, were growing and then melting, and that scoured away all this sedimentary material from beneath where the ice sheets were sitting and got down to this hard bedrock, and that made the ice sheets stickier so they would last longer. Or there's a third hypothesis that the big ice sheets in Antarctica compared to the ice sheets in northern hemisphere were varying at different times. So when it was really cold in the southern hemisphere, it might have been warmer in the north, and vice versa. And so the two hemispheres were out of phase. And the ice cores will allow us to test those things, which comes down to, why do we want to know answers to those sort of questions? I guess it's the fundamentals of how the climate system works, and they're quite sort of basic questions that can teach us the sensitivity of the Earth's climate system to things like changes in greenhouse gases, to things like the material, what's underneath the ice, whether it's soft or whether it's crystalline bedrock, and also to these sort of the way the climate system can sort of ping back and forth between north and south, and have these internal oscillations.
Yeah, absolutely. So what do you think is your favorite and least favorite thing about working in Antarctica?
Yeah, my favourite, I think, is just the pure adventure of it, and the beauty of it, and the starkness of it, and the fact that it's just so different to anywhere else on the planet. And so it's really beautiful. It's really clean. And I don't enjoy the cold so much, though. I'm actually someone who, like, my fingers get cold, they get numb. Your fingers on your armpits and all this sort of stuff. So I say that's but you dress well. We have good equipment, and even once you get inside a tent and you're sheltered from the wind, and you have a couple of big thick sleeping bags and a few sheepskins to sleep on, you're usually pretty comfortable in there. And there's also good being out there in a group. It's a good sort of team thing, and there's good camaraderie. We have pretty good fun out there.
Yeah, absolutely. For someone who doesn't like the cold, what is the coldest temperature you have experienced in Antarctica?
I think the coldest is probably pushing towards -40 when we went onto the Amory ice shelf.
That's
Yeah,
insane.
certainly below, and in Greenland we had some temperatures approaching -40 as well. Um, that's where, like, you breathe in and you feel it freeze inside your nostrils, and you really got to cover your face or you feel it starting to sort of freeze. But it's okay if it's still, but as soon as there's any sort of wind,
Mm.
it's really bites. Yeah.
So what sort of people, when you're talking about like team and working in teams and stuff, what sort of people do you work with in and outside of Antarctica?
So in Antarctica, it would be a handful of scientists, and then really important people that can maintain the camp, which is engineers, electrical engineers to help maintain the drill, and diesel mechanics because we usually have a generator there that's making power to power our drill and power some of the other things we use. Like, we still have to have computers and communications connections to the other Antarctic bases and back to home. And then usually in the field camps, there's often a trained sort of mountaineer person who's there for safety reasons. And then sometimes there's a cook, or sometimes we take turns cooking. Often there's someone who's a leader of the camp, but usually, there's only so many people that can be there, so we've all got to have multiple skills, and the camp leader might also be the mechanic or the mountaineer, or the scientist.
Yeah, absolutely.
Yeah.
So given the efforts that scientists across the globe go to extracting information that benefits all of humanity, in particular about the climate changing, amongst many other things, do you become frustrated when it is largely ignored by the mainstream media at the cost of increasing apathy and ignorance?
Yeah, I do become frustrated. I think what frustrates me most is there's sort of disconnect between where we're at with the science, and where some of the media and just mainstream, and some of the politics is. We've in the science, there's a lot of things that are really clear to us and have been clear for 20 years, and on many of these things the public hasn't got that yet, and I think that's very frustrating. Things like the fact that we really clearly know that our greenhouse gas levels are way beyond anything in the natural range, and that the rate of increase is 10 to 100 times faster, and that it's really clear just from the measurement of the isotopes that this is us. People don't know that, yet we've known that from the ice core data for 20 years. So that's frustrating. And then, it would be nice to see the clarity of the science translate into some more action. But, it's, as scientists, I guess all we can do is try and present the data as clearly as we can. And, there's a lot of other influences that come into deciding what happens with it. But I feel it's really important to communicate the data and the measurements as clearly as we possibly can.
Absolutely. So with what you were saying with people not understanding some of the science, I am 17 years old, and sometimes I'm not overly optimistic that people will grasp on the concept of the science, or I find that politicians will pick and choose what science they want to believe. Do you think there's any hope for humanity and the human race to start addressing climate change and accepting the science? Or do you think there is any cause for hope?
Yeah, I actually do see some quite hopeful things, and I think there's also enormous opportunities for Australia in it. Australia stands to be more affected than any other developed country by the impacts of climate change, through bushfires, through sea level rise, and through effects on some of our most important agricultural regions and the Great Barrier Reef. But Australia also stands to benefit from taking really strong action on climate change. We have huge resource for renewable energy with all the land area that we have that's available for solar. Compared to other developed countries, we have this huge coastline that's really suitable for wind power. And we have great scientists, and we're technologically advanced, and and we've got all these our mineral resources which we could use our green energy to process and to refine, and we could lead the world in a renewable economy. So there's hope there, and you see it starting to be pursued, and more power to those people. But the Earth can only take so much, and we're seeing devastating effects on the Barrier Reef and with the fires, and so we really need to get cracking, and what we do now is really important. Another thing that's frustrating is everyone's here, we've got 10 years to do it, and you might have heard, 10 years ago people said we've got 10 years to do it. Really, like, this year is important, next year is important, the year after is important. We can't push it back. What's important for the physics is how much CO2 goes up, and every year we put more up, the impacts on the climate system get locked in further and grow with each year of additional emissions.
Thank you so much for doing this interview with me. I really, really appreciated it, and I've learnt heaps. I could ask you tons of more questions, but I won't take up any more of your time. So thank you so much.
Good on you, Michaela. Thanks for doing this, and for all your work on communicating science and the environment.
Thank you so much. See you later.
See ya.